Yes. So, hello everyone. I'm Kato Stephen Magiro, a colleague in the regional Africa program at the Cohere Labs community, where we do open science, try to foster the AI research community in Africa. So today we are hosting one of our very own members who has contributed to projects. His name is Paul. I try to pronounce it sometimes and it was a bit hard.
Yeah, that's fine.
Yes, I Paul Okewunmi. So the
Yeah,
N.
you didn't do so bad.
Yeah, okay. So Paul has contributed to AfriAIA, which was a project we studied at Region Africa in the expedition AIA, and it's already hosted in the Cohere Labs community Hugging Face. So you're going to see posts today about it on the platforms, and so we're very happy. He was instrumental in that project where we tried to do multimodal AI for Africa, trying to give vision language models sight by working on an African data set that will be interesting. I hope all of you will follow the Cohere Labs page today night or during the day. It will be interesting. We've already put it out, but we haven't yet communicated. So Paul today is going to present to us his paper, which won an award. And personally, when I posted on LinkedIn about Paul, I realized a lot of people were really, really interested, especially from West Africa, in Paul's work. And so for that matter, I would like to give Paul the stage to talk about himself and to take us through his work.
Okay.
Thank you.
Thank you very much, Stephen. So my name is okay. Let me start sharing my screen. Okay. So my name is Paul Okewunmi. I'm from Nigeria, and I'm very much excited about today's event. Why? Because I'm also a Cohere Labs community member, and it's an avenue for me to share my recent research work. And also, I feel like this actually pertains to most of us in the Cohere Euro-Regional Africa group. And why? Because most of us are bilingual or speak our native language, and it will be more relatable. This topic is going to be more relatable to some of us. Okay, so a little bit about myself before I proceed. I'm exploring community-driven research. So I'm very much active in ML Collective, and also in ML Collective, yeah, I won't go too much into some of the projects I'm involved in, but for Cohere, just as Stephen has said, I'm involved in the AfriAIA project. Okay, so very quickly, I'm going to be going straight on to talking about the title. Um, and before I do that, I just wanted to point out that this is going to be sharing insights um, from my recent paper. The name of the paper is Evaluating Robustness of LLMs to Typographical Error in Yorùbá Question and Answering. And this was presented at AfricaNLP in July, which was collocated at ACL, and was one of the two papers that won the Best Paper Award. So here we try to look at a very simple but very much overlooked aspect of low resource NLP. Why? Because while we are mostly interested in we are mostly interested in how much of a difference a new model is from the last model, and we are assuming that the model is going to be so when testing on low resource languages, I think mostly we are assuming the inputs are going to be perfect. But most times it's not perfect. Why? Because before I even go into the reason, I just want to have a quick question in the chat. So if you've had an experience have you ever tried interacting with LLMs in your native language? So say Swahili, Luganda. So how many people here have tried interacting with LLMs, ChatGPT, Claude, whatever, in their native language? And how was the experience? Does anyone want to show of hands? Okay, so yeah, so in the chat, Steven is saying Claude, and Claude wasn't performing too well. On the screen we have three languages. We have so Caleb is saying ChatGPT. Yeah, ChatGPT very popular. On the screen we have three languages. We have Yorùbá, Swahili, and Luganda. I don't know if Steven, was this correct? So this is supposed to be how are you? Is this correct in Luganda?
Yeah, that is correct.
Okay. So I literally copied this from an LLM and posted it here. So I'm glad that is correct. But this is a very okay. So Kanwal talked about Odoo and he's struggling with so let me just see if I can read that correctly. Struggling with a lot of grammatical issues with Urdu or native language. So I'm very I'm happy that a lot of people can relate to this, irrespective of the fact that not everybody is speaking Yoruba. Yoruba is my language. Urdu is Kanwa's language. So everybody can relate to someone that is not speaking English or an resource language can relate to this. For Yoruba, the experience is this: you have the LLMs giving you good responses. So they're giving you good responses, but when you try to ask the same question in a slightly modified manner, it seems to just mess with the it messes with the LLM. So let me move on. And that was why my co-researchers decided to tackle this problem. Why? Because sorry, I'm having an issue switching. Okay, yeah. So the issue is most LLMs or chat interface, you interact using a keyboard. So say Gemini, say Claude, even VLMs, vision models, interact with them using your chat. And if you're using chats, it means the possibility of you typing the wrong thing or making typographical error is very high. And if these tools are going to serve, if these tools are going to be inclusive of or even try to be multilingual, because these large models are multilingual. Then we need to be able to evaluate when there's an imperfect input. So when the input is not the perfect sentence, what happens when the input is not the perfect sentence? So that is why we decided to tackle this problem. This is not a problem in English. For fear of stating the obvious, English is perfect. So I don't know if you've noticed, but if you make very terrible grammatical errors or you make terrible typographical errors, ChatGPT would handle your query like it's nothing, like you didn't make an error at all. But the same is not the case for most low resource languages. And let me give you an example in Yoruba. Not everybody understands Yoruba, but I'll try to explain to you. So Yoruba is a tonal language. It means we use tonal marks. So look at these three sentences, the third bullet point. You see that those three words, they are the same letter, if you might say. So they are the same OGUN, but because of the tonal marks, the meaning are completely different. So those three sentences, the first one means war. The second one means the first one is a deity in Yoruba. We call the deity Ogun. The second one is Ogun. Ogun means war. And the third one is Ogun. Ogun means 20. But you can see the problem. The problem is they are spelled in similar manner, but then they don't mean the same thing. So it means if you are to spell 20 and you spell 20 without the tonal mark or without the correct tonal mark, then there's a chance that there's going to be an issue with a model trying to understand that. Okay, so moving on. And before I move on, I just want to state that while we're doing Yoruba, just swap in your own native language, and there are different nuances for different languages. So I just gave an example of Yoruba, but I'm sure in your native language, there are things like this where the meaning of words are quite nuanced or based on the way they are used. Okay, so the research question here is now, how robust are these LLMs to typographical error in, I'll put a space, so in question answering for whichever language, swap in your language. And that is the main thing I'm going to be talking about on this call. On the right side, you see an example I put here, and the example here is with Claude, and it's quite it's a simple example. So I'm asking a question. I wish I put the English translation, but the English translation is, okay, what do you mean by a virtuous person? So who is a, like, can you tell me who is a virtuous person? Virtuous in the sense that the person is has very good virtues. By spelling that correctly, I get a very perfect response from ChatGPT. So from Claude, it gives me a correct response. But then where the problem lies is when I swap out some characters. So I made intentionally made some typographical error in this query. And if you can notice, I swapped out the O, although in Yoruba is O. I swapped out the O and I replaced it with P. I swapped out the A and I replaced it with S. And instead of UA, it is AU. And instead of O, it is I. So like I just made some very, very common, and you notice that these errors are common. Why? Because sometimes I want to I want to click on I on my keyboard and I click on O because O is adjacent, it's close to I. Or sometimes I want to type AU and I type UA because I'm typing fast. Or sometimes I want to type a letter once and I type it twice. And these are like ways you can introduce errors while typing. And I've stated before that in real world systems, we need robustness to imperfect inputs, and typos are imperfect inputs. So the paper focused on four things. First is a way to inject realistic noise in text, in Yoruba text. So a way you can, so if you say you want to gather real world Yoruba text, you might not be able to gather enough data. So one way we can do that is to generate synthetic noise by coming up with a probabilistic approach of imputing noise into sentences. And this helps us to build some sort of data set, and we try to evaluate these data sets, both the clean and the error injected sentence on at the time. These were like the state-of-the-art models when we wrote the paper, but now we have GPT-5, we have Gemini 2.5, and we have Claude Sonnet 4.0. So like things are moving fast, like we all know. And also we gave some insight on what a benchmark would look like if we have to create a benchmark for this problem. Okay, so next, the speaking of noise, speaking of typographical noise. So in the example I gave, I talked about swapping letters and I talked about introducing new characters, and this were the four types of characters of noise that we try to work with to just limit our scope. So there's an insertion error. So insertion error is you inserted a character okay, so you inserted a character when you're not supposed to. Say, for example, you double type, and you're working with the framework of a QWERTY keyboard. So the keyboard, the adjacent letters on your keyboard instead of the actual letter you wanted to type. A replacement error. Replacement error is basically instead of typing one character, you replace it with a neighboring character. Transposition error is the example I gave of swapping characters based on, say, you're typing fast instead of AU, you typed UA or something like that. And a random error. So random error was we trying to just see how we can push this, like push this far. Why? Because so I don't know if you know lit speak. So lit speak, if you're typing in, if you're writing in lit speak, it's you see things you see things like instead of writing S, you write a dollar sign, or instead of writing O, you write 0, or instead of writing I, you write 1. Those are like lead speak characters. So we try to just randomize and add those just to see how far this or how robust these models are. And for each of the errors, you can see examples here. So this is a clean. The first one is a clean sentence. Then based on each error, you see what is being done. So for replacement, K is replaced with L and things like that. Okay. So moving on. And how do we inject the noise? So we inject the noise by this pretty, I'll say pretty simple approach where you have a sentence and you want to vary the noise levels in that sentence. So you want to gradually increase the typographical error in that sentence, in the sentence, the percentage of characters that are affected in a sentence. What we literally are doing is, if you have a sentence, you split those sentences into characters. Although we call it text tokenization here, but then it's not the traditional tokenization we know as in training LLMs. But this is just splitting into characters. Then you have a probability P, which is the probability of a character being affected. So when we say affected means swapping that character with adjacent characters on your keyboard. So if you look at your I, you have U, O, and maybe J or K. Those are like possible characters that we swap with. So if P is 20, if P is 0.2 or 20%, 20% of the characters in that sentence will be affected. And we gradually increase that. We create new variations of the same sentence with increasing noise levels. So we have a clean sentence. We have that sentence when 10% of the characters are affected. That's 10% error rate, 20% error rate, 30% error rate, and the likes. Okay, so we decided to pick. So the reason why we picked 50 QA pairs was because the number of sentences increases exponentially. So if I'm starting with 50 clean question and answers, so these question and answers are chosen in the way in a form where there's one objective answer to the question. So for example, if I say 2 plus 2, the objective answer to 2 plus 2 is 4. So these are questions that are chosen in a way that there's no the answers are not changing ever. And you have 50 of them, question and answers, clean sentences. Funny thing is the clean sentences, when you give an LLM, the LLM gives you clean responses. So it gives you good responses. Then we introduce error into the sentences. We introduce 10%, 20%, 30%, and 40% errors into that clean sentence. So for each sentence, you have 4 variants of the 4 error types. And okay, of the 4 error types, insertion, replacement, and the like. And for each of those, you have 4 error rates. So 10%, 20%, 30%, 40% errors. And for each of those sentences, we try to generate 3 variants so that we can have something that is statistically significant. So we can we can take the mean of those three variants to actually tell to actually see the right signals and not just take one sentence and assume. Okay, so at the end we had 2,400 sentences, where only 50 are the clean sentence and the rest are error, typographical error prone sentences. And what we did was I skipped a slide here, and I think it was a mistake on my part. So what we did was you take a clean sentence and you take an error injected sentence and you ask the model. So say we are working with Claude. We ask the model we ask the model the question using the clean sentence. We get a response, a good response. Then we ask using the error injected sentence. We get a response. We don't know if the response is correct or not. Then we evaluate the answer to the wrong question and the answer to the clean question. So we compare them to see how different they are. And we decided to go with two evaluation strategies. One was BERT score, so measuring the similarity between those two sentences. But the issue with BERT score is you need very good embeddings. You need very good embeddings to be able to tell differences or similarities between sentences. And we used the multilingual model to generate the embeddings. We used the multilingual variant of BERT, so multilingual BERT. But the issue is, while it can measure similarity, it fails to reflect how dissimilar two Yoruba sentences truly are. So it gives you some idea that these sentences are different, but it doesn't give you like it does the value doesn't tell you how drastic that difference is. It just tells you, okay, there's a difference. So this means we needed some other way to evaluate these models. So we decided to go the LLM as judge approach, where we are using three metrics. No, okay. We're asking an LLM, which is Gemini 2.0, serving as our judge in this case. And we're asking it, given this good answer, giving the correct answer, and giving the answer from the wrong sentence, how was the fluency affected? Or how was the comprehension affected? Or how was accuracy affected? And things like that. Then there was also a metric called refusal rate. So these models, given how very good they are, instead of giving you a wrong answer, they'll tell you, "Oh, can you clarify?" Or "I don't think there's a word like this." So while it doesn't give you an answer, it tells you, okay, it doesn't understand. So that's refusal rate. While some models force themselves to give you an answer. So I'm going to talk about some results we got at the end in that characterize the way different models try to attack this problem. So we have a scale of 1 to 5 that is rating the fluency. Was the fluency affected? Was the comprehension affected? Was the accuracy affected? Or did the model refuse? Okay. So here are some interesting results. And I want you to take close look at the plots on the top, the first three plots at the top, and you see there's a particular metric that stays decently like high, almost to 40% error rate. So yeah, we have error rates plotted versus the scores we got from the LLM as judge. So we see that fluency is very like it's to a large extent the model stays fluent all through. Why is this why is this the case? So we noticed that even when the model, like I said in the previous slide, even when a model does, at least for Yoruba, even when the model doesn't have an answer, it tells you in a fluent manner that it doesn't understand. So instead of giving you wrong Yoruba sentence, sometimes it tells you oh, I don't understand this sentence, and it tells you in a fluent Yoruba. So that's why even as you increase the error rates, so the sentence gets more, the sentence gets higher in error, but then the fluency doesn't is not really affected. But then we see that at 20% error rates, all other metrics just takes a nosedive, and that is for comprehension, for accuracy, comprehension and accuracy. So at that, it seemed like 20% was like the breaking point, where at that point the models just couldn't comprehend what you were saying, and were misinterpreting and giving you a wrong answer. Okay, I added this other plot below because it shows what we got from the BET score evaluation metrics. Although I wouldn't, if you look closely, you see that the scores are hovering around 0.82 and 0.72. So it means it's the scores are high. So the scores are reducing from 0.82, giving you a bad score, very high bad score when you start increasing the error, and it reduces. So it reduces to like 0.72. But for the kind of drastic answers, like drastic difference between these two answers, 0.72 is still a very high score. So we're supposed to get something very, very close to zero. That's why bet score on its own was not used. So we had to complement this with LLM as judge. And we saw that LLM as judge actually shows that drastic nosedive in the model's comprehension and accuracy. So this is just interpreting what I just said, where at some point at 20% noise levels, the models stopped comprehending and stopped giving accurate responses. So they were giving fluent but confused response. So even if they tell you something different, they tell you that different thing in fluent Yoruba. And we noticed that replacement error was the most damaging. So cases where you're replacing characters, they're the most damaging. So if you look back at the plots, we see that replacement error. So replacement error is okay. I don't have that here. Okay, but I didn't have the plot here. We noticed that was the most damaging type of error for the LLMs. And while I talked about different models trying to handle the problem differently, so sometimes we notice different things for different models. So for GPT-4o, we noticed that it aggressively tries to attempt to answer the question, even if its understanding is very low. So even if you're at 40% error rate, where most of the characters have been affected, ChatGPT still, let's say ChatGPT, GPT-4 still tries to attempt to give you something. So it just gives you something. Gemini is always more cautious, so it tells you it had very high refusal rates. Instead of giving you a wrong sentence, it tells you it doesn't understand. Claude Sonnet also showed very strong comprehension at lower noise levels. So on the plot I showed for comprehension for Claude, it had the highest comprehension score for noise levels between 1 and 20, so between 10 and 20. But then it also degrades like the others. So while looking at these results, there's no one model that like shines and gives you a good result, and that's why it brings us into the question of there should be some sort of benchmark, or there should be some sort of benchmark or data sets that tries to evaluate imperfect inputs to LLMs for low resource languages. Some limitations with some of our approach was and also future directions. Synthetic noise is not all is while we can only try to simulate what synthetic noise is like, is not equal to real world typographical noise. So then it brings up the question, like, if you were to gather a large data set of typographical real world noise, then it means that you have to have a system where people are constantly interacting with their native language, um, and we going through all that to get the typos. That's one way, although that seems like a very yeah, it seems like a very challenging way to do it. Some other ways you could, although this in the sense is not typographical noise, but is also some sort of noise. So say in systems where you have speech to text. So say for example you're using ChatGPT and instead you're using the voice to text feature. It is also noise. We can't say it is typographical noise, but it's also some sort of real world noise types. So in translation from your language to ChatGPT, so for translation from your speech to text, in order to give these models, they just might be, definitely will be noise introduced because of low resource. We also started with 50 question and answer pairs. Although given I gave the I showed why the sentences could increase drastically, exponentially. Why? Because for each of those question pairs, you have 4 error types. For each of those error types, you have 4 error rates, and we're generating 3 different variants of those error types. Although yes, it's possible to have more and to actually see like larger trends in this idea. So we also had very limited human evaluation. So we had Yoruba speakers going through some subset of this 50 this question and answer pairs, and also the generated error questions. And ideally, we want to create a situation where majority of the outputs, the model output from the error prone sentences, from the error infused sentences, you have humans actually looking through and rating, or what the comprehension score was, or what the accuracy score was. Um, then bet score, like I talked about, was not optimized. It could be using better embedding models. We could try using bet score again if the embedding models are going to show very drastic difference between sentences. And also models keep evolving, so there's always need to reevaluate. So for example, when we wrote this paper, the best GPT model was I think 4.0, excluding the reasoning models, and now we have GPT-5. So how do we do we know if GPT-5 is more robust than GPT-4 on imperfect inputs when interacting in low resource languages? We don't know. So this is the reason why we need like a benchmark like this. Then also, could we replicate this to other languages? So this would be some sort of very good community driven project where, based on the unique characteristics of your local language, of your native language, can you try to generate realistic imperfect inputs, and can you try to evaluate the models on those inputs using the methodology that we've laid out in this paper? Okay. So in conclusion, we've showed how sensitive, we've quantified how sensitive models are, at least the top 3 ones. We didn't try open source ones, but we tried to look for pick the best models, even open source or proprietary ones. And we've shown how this noise affects these models. And we've seen a very large research gap. Why? Because while we are trying to improve the performance of these models, we also need to evaluate them on imperfect inputs in low resource settings. And we've also, so doing all of this, we can truly get useful models. So useful models that can scale in the real world. Or say you're building a startup. So I know we have different startups building tools using using these models for low resource population. So for like a place like Africa, where you have people building tools that are going to be used by people who can speak English properly or who can't speak English at all, then it becomes very, very paramount where we need to know the behaviors of these models when it is imperfect. Thank you very much for your attention. I really hope I was able to share very good insights. I'll take questions now. Okay. I don't know if I'm getting the name correctly. Tani.
Yeah. Hey, Paul, how are you doing? I really enjoyed the presentation, so thank you so much for spending the time to present it to us. I had three questions, but I'll go through them one by one. So, the first question I had was, do you think that just this heuristic or like, this kind of methodology of like checking for, typo errors and seeing how that affects performance is like a good, meta metric for just understanding how low resource a language is or how bad the performance of a language is? Like, I know that if we do this kind of experiment with a much higher resource language like English or Hindi, the performance will be much better, right? So do you think it's also like a metric we can use to just understand how bad performance is in general for a low resource language?
Okay, so is that the only question, or should I answer this then?
Oh yeah, if you can answer this first, then that'd be good. Then I can come to the next one.
Okay. So from my point of view, I think this should be like we need more. So yeah, so your short answer is yes. I think this can be used to evaluate performance of models on low resource languages, and the reason being, there were chances where we thought about using some native LLMs. So there's a model called there's a model from Lelapa AI, a South African company. They built a native LLM, and the performance don't even come close to your ChatGPT and Vula, yeah. So the performance don't come close to your ChatGPT or your Claude or your. So we didn't even bother going in that direction. And even given that we've taken the best of these LLMs, we still see like very simple perturbations in this input gives you like totally wrong answers. So I feel like we are not looking not a lot of people are looking in this direction. More people should be looking in this direction. I don't know if that answers the question.
No, that does. That was great. My second question was on the LLM as a judge part of the whole experiment, right? So I wasn't able to go through the whole presentation. I was kind of out of the call, but because the LLM itself is also kind of bad at the low resource language, is there like a confounding factor that like it will perform poorly even as a judge, or is that not a point of concern?
Okay, so yeah, so the reason why we're using LLM as judge, also noting that we want to evaluate these models on this problem. So when you give perfect inputs, these models perform like brilliant. So they give you brilliant results. So if an input, I can speak for you for Yoruba, which is my native language. So you properly intonate your sentence and you give a correct sentence, you see very good results. So meaning it's not the understanding, it's not the basic understanding that is lacking. So they understand the basics. So it means they can tell you that these sentences are wrong. So they can give you one. So they can tell you on a scale of 1 to 5, these sentences are not similar. They can tell you on a scale of 1 to 5, comprehension is not the same, and things like that. So, but just that when you now take a clean sentence and you just make simple perturbations, then that's where the problem comes.
Yeah, that makes perfect sense. My last question was on the probabilistic algorithm that you use to kind of induce the noise in the data, right? So for this algorithm, so could you like speak more about it? Are you trying to kind of replicate the kind of typographical errors which humans come up with, or how did you come up with this algorithm in general?
Okay, yeah. So this was um, just an effort to try to replicate real world typographical errors. So and that is based off of the keyboard. So we have the way these errors are introduced is based on adjacent keys on your keyboard. So if I'm to do, say for example, a so for insertion and insertion and replacement errors, if I'm to replace a character, I'm replacing an I with an O, or I'm replacing an E with an R because they are adjacent on the keyboard. So I'm doing that because like I'm just trying to simulate what characters would actually, like what kind of errors you'd see when you type. So the probability is just how many of the characters will be affected. But then I just explained what characters might be used in place of what you remove, things like that. So when you start going way higher than 40%, then it becomes garble. It becomes gibberish, and even native speakers won't be able to tell. So, but even at very high error rates for English, even when you can't say even when you can't say what the sentence is, sometimes these LLMs are even able to give you good response. But yeah, the same is not the case.
Makes sense. I'm sorry, I had like another like question related to this, if you mind.
Okay.
So my question was, uh, like, how do you come up with like the like each of the probabilities, or like, it, is it just random? Do you think it will benefit more if we had like a different model, which where like the probability of an error being introduced into one of the letters is actually dependent on the previous letters which have already been kind of put in the sample, because
Uh,
that would kind of replicate how humans make errors better, I guess.
yeah. So this question is like, it's very important because we some of the reviewers pointed this out. And what we actually doing is so what we try to do is we create three variants of the same, like, so running this algorithm we create three variants, but even in those variants we are taking each word and we are so say for example I've sampled, I'm doing things randomly, so say for example I've sampled from this word. For the next variant, there's a chance that I wouldn't sample from that word in the sense from a particular word. I might sample for the next word. So while we didn't control if the first character sample affects the second one or the third one, what we just tried to do was let's create three variants of using the same probability. Just create three variants of these things and at least three examples of different generations of this error injected sentence would would like try to tackle the problem of, oh, do you want to make one character depending on the next and the next? And I don't know if I answered that question.
No, that makes sense. Yeah, makes sense.
So
Uh,
uh,
thank you so much, and
yes,
congratulations on such great research.
yeah. Um, thank you very much, Annie. Do you have any other question?
Not me. That was great. Thank you so much.
Okay.
All right. Thank you so much, Paul. Just to add a comment, I was also surprised by the model by the developer. I thought, that maybe training from scratch to perform well. Just this week, I asked someone, but you know that there's this model and no one is using it, and they were surprised. It was a researcher in Kenya, it's built from scratch, and also
Yeah,
I've seen researchers in Kenya who have done such work from scratch. Swahili, no one dares to use those models.
yeah. The models are not as useful as we might want them to be. So
Yes.
I was very excited when the model was released. So they released it, and it was supposed to cover about five African languages. And one of the things I even read was sometimes the model switches between languages. So it's not it's not yet at the stage would want them to be. I know someone did a work on um story generation. So like I know, although this is just narrowing down to just one sentence, not trying to complicate things. Someone built a very small model, so in the range of about 150 million parameters for generating stories in Yoruba. So the person took tiny stories, the very popular tiny stories data set, converted it to Yoruba, and trained a small model for story generation. And from what I saw, the stories were very, very good. So if it's possible to do that, I feel like maybe with and the translation was it was translation. It was the stories were translated from Yoruba, from English to Yoruba. So which means the data set is synthetic, because tiny stories is a synthetic data. I mean, it introduced like some questions of, I think, um, generating synthetic data, verifying that those synthetic data are somewhat representative of the way we write, or the way we write low resource languages. Maybe we shouldn't be looking at the big models that can do everything, and instead we should be looking at just very niche models that can only speak Yoruba, can only speak Swahili, and can do it better than the very large models, the billion parameter models. It's just something I was thinking about, but yeah, um, these models I've never gotten to that point.
Yeah, you're right. So besides Cohere Labs, I know we have 5 minutes. We worked on a model for Uganda, where in sort of a small startup research lab with me and my team, some of them are in the Cohere Labs
Yeah,
community.
is it involving Bronson? I know Bronson shared some.
Yes. Yeah, and the model was beating a lot of the big models, the Clouds, the Llama, Maverick, GPT-5, and so we've realized that you can make a one big model speak your language, and it's really good. So what you're saying is very, very right. There are some other people who have tried to do multilingual in East Africa, still failing, because of the things you're saying, code switching and things like that. Bronson did most of that testing of code switching and a lot of things, and that's why the models presently are doing well.
Yeah,
But that's the best use case for Africa, because our infrastructure is even way old. So there's no way you're going to put it on a big data center when we have power issues and things like that. So realistically, us on ground, that we know these models, big ones and multilingual, they may not work for our low resource settings.
yeah, I agree with you. So instead of like thinking of doing too many things at the same time, like you said, the model you fine tuned on Gemma was performing better than GPT. Was it GPT-4?
Right.
Yeah, better than GPT-5. So yeah, I feel like we might want to start with just one model for our use case, then maybe scale up to multilingual and things like that.
So the main, also, sets where Africa is based on regions, and in each country you have different ethnic groups, and so you wouldn't want them to, type in one language, one comes out. So for us, we know that one model for one language is the best option. Maybe use a model router to switch if at all you're a service provider, but you always build a model for a language to avoid complications where I ask in this language, it replies in their language, and I'm in my region, and I'm like, okay, we have those sovereignty issues even internally in African countries. So, yeah, you've given us a really, really good presentation, and thank you so much. So let us clap for Paul, for those who are remaining on the call, and Paul has helped us on the AfricaNLP project. This project won an award in the expedition. Today it is hosted under Cohere Labs, the first project that we, the Region Africa community, have contributed to the Cohere Labs community, fully backed by Cohere Labs. So it's a wonderful day to host Paul and also to release our work. So Paul, thank you. This is going to be hosted on the Cohere Labs channel, actually the Cohere channel itself. And yeah, we look for more. Paul, if you have more research and more people you want us to host, just always reach out. We would be happy. So thank you so much.
All right. Thank you for having me.